So you've got your test there. If you've received a test and you compare it with the model answers that are given on the web, and you're not happy about the marking, bring your test to the tutorial on Mondays, where my assistant, Dr. Banerjee, is there. He's the guy who marks the tests. I will mark your exams, but we have assistants to mark the tests. So if he's been harsh, or sometimes there's an alternative method, like somebody showed me an alternative method that they followed, it might be clumsy and long and stuff, but if the answer is right, we can't take away the marks. But sometimes the one marking it may not be experienced enough to know it's the same thing. So if you believe that something is not right, you're welcome to come forward. Right, so last Monday I wasn't there at the tutorial, but I told you in advance I'm not going to be there, so I hope you didn't turn up there and swear me for not being there. But we have been there for all the other tutorials. We were at a conference, a general relativity conference in the Salt Rock Hotel. It was quite an interesting conference because they had some mathematical biologists also present. We were relativists, astrophysicists, cosmologists, a mixed bag of people who don't actually do the same work. The people were asking us things like, to solve Einstein's equations, you have to make certain assumptions and stuff. So I was trying to tell the biologists that sometimes you have to think in a non-standard way. You can't think in a straightforward way because Einstein's general idea was not typical. Unlike Newton, this apple story happened and then he conjectured that things fall towards the Earth, not away from the Earth. That's the law of gravity. Gravity is a force. In Einstein's general theory of relativity, gravity is the curvature of space-time. That's a deep, deep thought. Some authors say this is the most profound thought of a human mind ever. It's quite a deep thing to say, most profound human thought. It's not a standard mathematical thing also, curvature of space-time. So I gave this biologist an example. I said to him, there's a famous joke. The question was asked to some important personalities. Why did the chicken cross the road? You know the old, why did the chicken cross the road jokes? So they asked Robert Mugabe, and he says, if a chicken wants to take over a piece of road, that's his business. Then they asked Mr. Mandela. He says, well, it's a democratic right of chickens to cross roads. We should not question their motives. Then they asked Professor Einstein. Einstein thinks a bit and then he says, did the chicken cross the road or did the road move from under the chicken? That's the central idea in GR. It's a curvature of space-time. The chicken may have stood still, but the road changes curvature. So it's a neat trick. All right, now let's take this example here. Now you see this example is just find an integral, like a first-year calculus problem. And you may say, wow, let's hit this with, what do you call that, improper integrals. Take the limit, put a here, b here, make a go to infinity, b go to minus infinity, then we are in business. You're right, you can do it that way. I'll just do it in the method of the residue theorem now, just to confirm it works the same way, okay? So according to the residue theorem, we can say, consider, you don't have to write all this, but say consider f of z as 1 over z squared plus 1. And then the poles are when the denominator is 0, z squared 1 is 0. This means that z is equal to plus I or minus I. I squared is minus 1, so minus 1 plus 1 will give you a 0. So if you plot the poles, the pole I is over there, and the pole minus I is at the bottom. Remember, it's 0 plus I, 0 minus I. 0 plus 1I mean that the coordinates are 0, 1. That's why it's 0 on the x-axis, 1 on the y. 0 minus 1, 0 on the x-axis, 1 on the y. That's the position of the 2 points there. Then you will recall I said that the trick is now to surround this guy with a semicircle contour. And why that works is because the integral along that is going to be 0. You can have minus r to plus r, doesn't matter. So then we've got the denominator having a power higher than the numerator by 2. That's what the game requires. So then you can then say the integral of minus infinity to plus infinity. You can replace this by 1 over z squared plus 1 dz. It's exactly the same thing, like a dummy index, changing x into z. But the answer is 2 pi I residue of 1 over z squared plus 1 at the point z equals I only. Now, how do you work out the residue? 2 pi I residue of. So one trick, I mean, remember, this is going to be like 1 over z plus I to z minus I. So you could say 2 pi I residue of, I want it at z equals I. So let me take 1 over z plus I on the top, all over z minus I. I make that disguise. This becomes like the g of z. Remember the 4 cases I dealt with? The second one had g of z over z minus a. So the residue in that case is this g of a. You plug in I there, becomes 2 pi I times 1 over I plus I. That's it. At z equals I, of course, right? So it's 2 pi I over 1 over 2I. Answer is pi. Now let's check it with your technique. Integral minus infinity plus infinity of 1 over x squared plus 1 dx. What is the integral of such a thing? What's the integral of 1 over x squared plus 1? 10, arc 10. Arc 10. Okay, so it's arc 10 x. And the limits are minus pi, minus infinity to plus infinity. So it's arc 10 infinity minus arc 10 minus infinity. Arc 10 infinity is pi over 2. We know that at pi over 2, tan graph becomes infinite. Minus arc 10 at minus infinity is minus pi over 2. So pi over 2 plus pi over 2 is pi. Checks out. That one can be done this way. You can't do it, you can't always do things that way. Sometimes you just can't integrate. Okay, so that verifies the thing has hope of working. It does have some hope, it's true. The bottom line is that this guy was done without any integration. This guy, you had to know the integral was arc10. If you don't know the integral, then you're stuck. So let me take one now where you will get stuck. Similar one, but I just put this in here because I was reading somewhere that this integral appears in statistics. Integral of e to the ikz. We can call it x. In other words, these are real values. Ikx over x squared plus 1 dx minus infinity to plus infinity. I don't know much statistics, but I believe that appears in statistics. Certainly the denominator, well, the numerator is always positive. So perhaps it's got, I can see why it appears in statistics, because it's got this Maxwell-Boltzmann curve. On the negative side and the positive side is exactly the same y values. It will be like that. It would be like an even function, something like that. Perhaps. So we can use our theorem since e to the ikz is an entire function. No poles. Entire function means it has no poles. Poles will only be at z squared plus 1 equal to 0. Remember now I'm transforming from x to z. I said that you can treat the x as z. So you can apply complex methods. We just disguise the x into a z, who knows? I mean, go back and then quietly put the z back as x. The answer will be the same. Z squared plus 1 equals 0, so again, z equals to plus minus I. Same story again. Identify the two poles, I and minus I. Throw a semicircular contour around them. So you can say integral of e to the I k z, so z squared plus 1 dz, minus infinity plus infinity, is in fact 2 pi I, the residue of e to the I k z over z plus I into z minus I. And remember, only z equals to I counts, because the minus I is outside of it. It's not in the contour. Upper half of the plane. This follows the same thing as what we've done already, right? So it's 2 pi I residue of e to the I k z divided by z plus I, all upon z minus I. I'm setting it up into a g of z over z minus a. That's what I'm trying to do with disguise, as z equals I. So it's 2 pi I. Substitute I in the top, it's e to the I times k times I over I plus I. It's 2 pi I times e to the I squared is minus 1, so it's minus k over 2i. The answer boils down to pi e to the minus k. Okay, pi e to the minus k. It's a real number answer. There's not any sign of I anyway. There's no complex number. So this is the same. This is going to be the answer for the integral of e to the I kx over squared plus 1 dx. Like z and x are like dummy variables, interchangeable. Look at that neat technique. Now, if you want to double check that, now you can't do it because you can't integrate this guy. You know what method of integrating this? The previous one I could hit that with R10. This one has got a spoiler here, e to the ikz with this z squared plus 1. So you can't integrate it. There is no known method to integrate this. But despite not knowing a method to integrate that, I was able to integrate it. It's simply pi e to the minus k. K is some number. So if it was like e to the 2iz, the answer will be pi over e squared. Big number, pi over e squared, which is a number. And that, you see, if I go back to real functions, think back to real functions. I don't know what this thing looks like, right? But let's say, I don't know what it looks like. But let's say something like this, something like that. I am actually finding the area underneath this thing here from minus infinity to plus infinity. That has a meaning. Integration of real functions has a meaning. It's an area underneath the function. I told you that integration of a complex function is not the same thing. Integration of a complex function is like two line integrals. But there's an uncanny connection between the two. With this residue theorem, we can now resolve integrals of real functions also for free. That's a spin-off of this theory, which is what I call a very beautiful part of the theory. All right, another example. Now, these are typically exam type examples. You'll get a question like this in your exam for 10 marks or 8 marks or so. Lots of work to be done, yeah? You have to find the poles. Sometimes finding the poles is the first part of the problem for students. Can't find the poles, the game is over. If you don't know how to use the Morgan's theorem, Forget it, pack up and go home, because the rest of the problem can't be worked out. So let's take this example 61. Find the integral of x squared over x to the 6. Oh, okay. Oh, this is a harmless one. X to the 4 plus 1 dx. Minus infinity plus infinity. You know any techniques to integrate that from first year? X squared over x to the 4th plus 1. Actually, there are some techniques. You can always factorize x to the 4 plus 1. It's not a difference of two squares, but it has complex roots. X squared minus I into x squared plus I, and then you factorize again. Then you can have 4 linear factors. Use, actually you can't use partial fractions. Maybe you have to have two quadratics and then do a division into a quadratic. Remember some questions like that in first year, where you have to divide the denominator into the numerator. So that's quite heavy lifting. I don't want to go there. Let's hit this with our normal techniques. So let's start off with the poles. The poles, the only place this function could be badly behaved is where z to the 4th plus 1 equals 0. You've got to find the poles, find those solutions of that. There should be 4 answers. Z to the 4th will have 4 roots, up to 4 roots. So now this is where you may get stuck in the exam, so that's why I'm going to spend some time doing the first example carefully. So z to the 4th is equal to minus 1 plus 0i. Take the 1 across. So if I plot minus 1 plus 0i on the Argand plane, it's here. So the angle theta applicable is pi. Applicable angle is pi. So z is the same as r e to the I theta to the power 4. This thing here, the radius is 1 e to the I. The theta here is pi plus 2k pi. This happens every 2k pi. So if you compare the two sides, you can say the r must be 1. R to the 4 is 1, r is 1. Clearly r is 1. And by the Morvis theorem, of course, 4 theta is pi plus 2k pi. The theta is pi over 4 plus k pi over 2. You divide by 4. That's theta. So the first root, z naught, will be 1 e to the I theta naught. So it will be e to the I. When k is naught, theta is pi over 4. So the first root will be e to the I pi over 4. The second root, z1, will be e to the I. Now put k equals to 1. 1 half plus 1 quarter. That's 3/4 pi. So it's 3/4 pi. Z2 will be e to the I. Now put k equals to 2. 2 over 2 is 1. Or you can say it's 4 over 4. 4 over 4 plus 1 over 4 is 5 over 4 pi. 5 over 4 pi. And Z3, oh, why am I saying Z cube? Z3 is e to the I. Now put a 3 here. 3 over 2 is the same as 6 over 4. 6 plus 1 is 7 over 4 pi. 7 over 4 pi. That's it. What will happen if I go to Z4? It will now start a cycle. You'll get the same answers again. You'll come back to the same thing. If you take Z4, you'll come back to Z0. If you take Z5, you'll come back to Z1. Same thing. because it will have a difference of 2 pi. You see, if you put z k equals 4, 2 pi over 4 pi over 2 pi is 2 pi. You're taking pi over 4 plus 2 pi. Isn't it back to pi over 4 then? 2 pi is one full circle. It comes back to its start. So there are only 4 roots. If you had to plot these 4 roots, so one angle is pi over 4, a radius of 1. So this is the first one, e to the I pi over 4. And the next one will be e to the 3/4 pi. 1 unit away. Then one will be here, and one will be here. So those are the 4 fourth roots of -1. Or if I put them down here, because I want to do the calculation now, there's one there, one here, and one here. This is e to the I pi over 4, e to the I 3/4 pi. Those are the only 2 important guys, because I then surround this guy with a contour, semicircular contour, minus r to plus r. I know the integral along CR here is going to be 0. You see that first part, how important it is, getting these roots? Because now you're going to be substituting these guys in the residue. So if you don't get these roots first, there's a problem. Observe how they are symmetrical. That must always happen. I said the bottom will have an even power. So you will always have conjugate pairs. You must have a reflection of the top at the bottom. So your integral that you wish to calculate now, integral of what is that? X squared over x to the 4th plus 1 dx minus infinity to plus infinity is 2 pi I times the residue of f of z at z equals to e to the I pi over 4 plus the residue of f of z at e to the I 3/4 pi. What happened there now? Why is it looking funny? Okay, in other words, so this works out to be 2 pi I need the residue of, you see f of z is z squared over z to the 4th plus 1. Which of those residue finding methods applies here? Something over something, p over q. Remember, p of z over q of z. Just check back and what is the technique if you got one polynomial divided by another. Isn't it p of q over q dash of a? P of a over q dash of a. I'm using the third technique, p of a over q dash of a. So I will find the residue of z squared over 4z cubed. Z equals to e to the I pi over 4. Thing is getting a bit wonky here. Plus the residue of, same thing again, z squared over 4z cubed. Why am I taking 4z cubed? The derivative of the denominator, guys. Q dash. Remember I said x behaves like z. Differentiate the denominator is 4z cubed. So you'll find it cancelling off now. Something wrong with the software here. Things are shifting. It's like the chicken and egg problem, chicken and crossing the road problem. 2 pi I Right? So, sorry, you don't have to write the word res there because we are finding the res already. When we start doing the differentiation, we are en route to finding the z. We just have to substitute. So we just have to substitute 1 over 4 z, and we have to plug in z equals to e to the I pi over 4 there, plus 1 over 4 z, because z squared cancels off with z cubed, there's z left there, and this time we have to substitute z equals e to the I 5/4 pi. No, 3/4 pi. So finally we can conclude this, 2 pi I over 4, we can say this is pi I over 2 for now, 1 over z, so this will become e to the minus I pi over 4, plus e to the minus I 3/4 pi. 1 over z, so you put z to be this, but because it's 1 over z, it will become e to the minus pi over 4. Likewise here, 1 over z, the minus I 3/4 pi. This 4, I put him out in front here. The 2 over 4 becomes pi I over 2. Now let's try to simplify those guys. So that's pi I over 2. This thing is like cos minus pi over 4 plus I sine minus pi over 4 plus this is cos minus 3/4 pi plus I sine minus 3/4 pi. This is simplifying it now. Sometimes you can go a few steps. Pi over 2I. Cos of minus pi over 4 is 1 over root 2. Sine of minus pi over 4 is minus 1 over root 2I. Cos of minus 3/4 pi, all sine, tan, cos. Or is cos of 3/4 pi. It's minus 1 over root 2. Sine of minus, that's minus sine. It's minus 1 over root 2I. Applying my high school techniques. Kill that. Pi I over 2 times minus 2 over root 2I. I times I is minus 1. Well, the 2's can cancel off. So it's pi over root 2. Is that right? Yeah, that's correct. So that integral works out to pi over root 2. I know you can't wait to go home and try out this alternative technique. Go back and look at your first year calculus book and see what technique you use to get x squared or x to the 4 plus 1. Just looking back at this, you'll see that the substance of this is to work out the poles. Then you only take the poles in the upper half plane, surround them. There is 2 pi I residue at those 2 poles. How many poles here? So I'm not going to do a full example now because of time left. But let me just pose to you this problem here, and you can try this out at home. I will deal with it in the next lecture. It's slightly different from an example in the book. Example. This is not a book one, but it looks the same. Find the practices. Find the integral of x plus 1 over x to the 6 plus 1 dx minus infinity. Oh, sorry, x plus I. That's the difference. The textbook has got x to the 6 plus 1. I made it x to the 6 plus I to put you off those normal roots. But note, one dirty trick here is that this is equal to the integral of x over x to the 6 plus I dx plus integral of 1 over x to the 6 plus 1 of I, sorry, dx, and this one here, this part is 0 because it's odd. So all you need to do is work this part out. But if I didn't say that, you'll get stuck with the problem. So who says lecturers are unkind? I've made it easier for you. Now all it does boils down to this part here. Try to crank that out. There will be 6 roots, 3 of which will lie on top, 3 below. Nothing will lie on the x-axis because we said it has no real roots. Okay, let's stop there.